Hi, I'm Michael Osman of Great Scott Gadgets, and this is Software Defined Radio with HRF, Lesson 2, DSP. In this lesson we'll begin an experiment that will help us understand the mysteries of digital signal processing, or DSP. But first let's review the homework from Lesson 1. The first thing I asked you to do was to download Pen2 Linux and give it a try. Because you can install the ISO image from Pen2 on a DVD or a USB flash drive, and boot your computer from that ISO image, Pen2 makes it very easy to run all of the software that you'll need for the exercises in this course. Even if you already have the software running on a different operating system, I encourage you to download Pen2 and give it a try if you haven't already. One of the things that it allows you to do is compare the way your software works with the way it works in Pen2 and verify that everything is working correctly. Also, it's really nice to have a complete Linux distribution with all of the software that you need for software-defined radio in a small package. I personally always travel with a Pen2 ISO installed on a flash drive, and then no matter where I am, I can plug that flash drive into a computer and plug in a HRF and do demos or show people how things work or just experiment. Now let's take a look at the remainder of the homework from Lesson 1. I asked you to take the flow graph that we made in Lesson 1 and enhance it in a few ways. Here's the flow graph that we created in Lesson 1. It's an FM radio receiver, and let's just make sure that it still works. Looks like it's working okay. Now the first thing I asked you to do was to add a slider to allow control of the frequency or the station that we're listening to. So I'm going to take my channel frequency variable and I want to turn that into a slider. I will just copy and paste this slider and call it channel freak. Now the original channel freak had a default value of 96.5 E6 or 96.5 megahertz, so I'll give that the default. I'm going to set the minimum to 89.9 or no, 87.9, which is right at the bottom of the FM broadcast band. I'm going to set the maximum to 107.9 E6. And it just works out that if I have 100 steps, I think that's going to be quite convenient for the number of radio stations and their channel spacing. Now I have an error in my flow graph. These blocks are angry at me because there are two things called channel freak. So I'll just delete this one, or we could disable it. And now let's see if this works. There's that other very prominent frequency, and this looks like it's working very well, and I can tune all the way to the top or the bottom of the band since I'm using 20 megahertz of bandwidth, or I have the sample rate set to 20 million. And this channel spacing nicely agrees with this 20 megahertz wide slider divided into 100 different steps. So now let's take a look at the second thing I asked you to do, which was to make this flow graph allow you to listen to two stations instead of two simultaneously. So in order to do that, I'm first going to delete this block, get it out of my way, and I'm going to just move things around a little bit so that I can just make room for what I want to do here. I'm going to take this FFT sync and move it out of the way. I'm going to put my multiply block up there and just kind of move everything closer together up near the top of the screen, hopefully allowing me room to do what I want to do. Now I have an audio gain control for this channel, and I have a channel frequency control for this channel. So if I want to be able to control both those things for my other channel, I should group those together. And now I should be able to copy and paste. Let's see, sample rate should be the same for both, center freak should be the same for both, channel width should be the same for both. Everything that I want to copy and paste is right up here. And actually I'm only going to have one audio sync because I only have one sound card. So I'll just take all this stuff and copy it, paste it. Now, my flow graph is starting to get a little bit more complicated, but if I take this output from the Osmocom source and run it to this new multiply block, it's a little hard to position everything so you can see all of the digital signals going from one block to the next. But now I have everything that I need, except this multiply const now goes to nowhere, and I'd like to combine it with the output of this multiply const. So what I'm going to do is go take a math block and add, and I'm going to simply add these two streams together. I'll get rid of this path by clicking on it and dragging away. Connect these two multiply consts to this add. I'll just scroll over here a little bit and then connect the add output to the audio sync. Now everything's happy except for a type mismatch. These have the floating point orange type, and this add block defaults to the blue type. So I'm going to go into the properties and change its type to float. Now everything's happy. However, I do want to go in and change a couple of things. Now notice it automatically renamed blocks for me. Like this one was called audio gain. This one became audio gain _0. This one was channel freak. It became channel freak _0. So I should probably rename things. And in fact, I'd like to rename things channel 1 and channel 2. So I'm going to go in here and change this one to audio gain 1 and this one to channel freak 1, and that will break some things. Now over here I need to set this signal source to channel freak 1 and this multiply const to audio gain 1, and that should give you a clue of what we're going to do next. Let's set this signal source to channel freak 2 and this one to audio gain 2. I'll call this slider audio gain 2, and I'll call this slider channel freak 2. Now I think everything matches the way I want it to. The only thing that might be nice to change would be to have these not default to the same channel frequency. I'm going to set the second one to 98.5 because that was the other very strong signal that I have in my neighborhood. I'm also going to set the audio gain default to 0. So I'm only listening to one station when I start up the flow graph, and then we can verify what happens when I turn up the gain of the second station. Let's give this a try. Okay. I'm listening to one station, and if I turn up the audio gain for the other, that's the other station. If I turn them both up, it might be a little hard to listen to, but it gives you a little bit of an idea of what we can do by tuning around in software. And there you go. Now we have a flow graph that allows us to listen to two different stations simultaneously. And HRF allows us to do that because it can give us 20 megahertz of bandwidth based on this sample rate, this 20 million samples per second maximum sample rate. And even if on your particular hardware you're not able to get 20 million samples per second, you should be able to get several samples per second. Several million samples per second, and that should allow you to listen to more than one FM radio station at the same time. We could even enhance this flow graph to let us listen to more than 2 stations. However, I would probably run into the limit of my CPU power, and also this flow graph would be overly complicated, but there are some ways that we could, maybe outside of GNU Radio Companion, make an array of blocks and that sort of thing to allow us to deal with many channels at once. We've just created a pretty complicated flow graph. There's a lot going on in there. And eventually in this course you'll learn the internals of every single block in that flow graph, how it works, and why the flow graph as a whole is able to accomplish the task of taking a radio signal and turning it into audio of 2 different FM radio stations without even retuning the front-end radio hardware. Now, I'd like to take a step back and think about the basics of digital signal processing, or DSP. You're probably familiar with the concept of an analog signal or a continuous signal, something that we draw as a continuously varying function over time. Radio waves and sound waves are examples of things that we typically think of as continuous signals. A digital signal is similar, except that it's made up of discrete values at discrete points in time, and it's typically drawn as a series of dots with stems extending to the horizontal axis. The horizontal axis is usually time. It doesn't have to be time, but for software-defined radio, we're almost always dealing with digital signals that are from the time domain, or at least originated as time domain signals. And I will sometimes draw these digital signals as a series of dots. I'll usually skip the stems, although they're traditional, just because they take more time to draw. And in fact, I'll often draw individual samples or individual values of the signal as an X instead of a dot, just because it's a little faster. Now I say sample because each value is often something that was arrived upon by measuring an actual continuous real-world signal, and that process is called sampling. So in HRF, there is a sampler, or an analog to digital converter, that takes an analog waveform, samples it or measures it at discrete periods in time, and then gives us the value at each sample point. Now, every value is a number, so fundamentally, a digital signal is simply a sequence of numbers. And there isn't a whole lot to digital signal processing fundamentally. If you think about it, all it is taking sequences of numbers and manipulating them in various ways. However, there is a whole field of interesting algorithms and interesting effects and different ways to manipulate digital signals. And I think you'll find that the field is very deep, even though at first it may seem like it's a very simple thing. And to get us started in exploring the mysteries of digital signal processing, I'd like to start with an exercise. And we're going to expand on this exercise and have some questions about it for our homework for this lesson. I'd like you to open up a new flow graph in GNU Radio Companion, and you can do that by clicking this New button, or by going to the File menu and selecting New, or using the keyboard shortcut Control-N. Now we have a new untitled flow graph, and I'd like you to start with a waveform generator. This will be a signal source, and the defaults are fine. 32 kilohertz sample rate, or 32 kilosamples per second, that comes from this variable here. Cosine, 1 kilohertz frequency, an amplitude of 1. Now I'm going to run this through a throttle block that comes from the miscellaneous section, and connect these two together. And then we only need one more block in our flow graph to get started, and this will be an instrumentation WX GUI FFT sync, just like we use to visualize the FM radio signals. And the defaults for this block should be fine too. So this is a very simple flow graph to put together, And let's just start it up and make sure it works here. I'll execute the flow graph. It prompts me for a file name. I'll call it lesson2.grc. And here we go. The FFT shows us one spike. And that's all we get. For homework for this lesson, I'd like you to take this simple flow graph and experiment with it and answer a series of questions. Go to greatscottgadgets.com/SDR, and under Lesson 2 you'll find the detailed description, the list of questions that I'd like you to answer. And I think that this is going to open up a lot of doors to interesting questions and thoughts you might have about digital signal processing. In the next lesson, we're going to go through and try to make sense of what this flow graph does when we manipulate it in different ways. And this is really going to set the stage for several lessons to come in which we'll explore the mysteries of digital signal processing. So I hope you'll do the exercise, the homework for Lesson 2, and I hope you'll join us for Lesson 3.